Okay, so here we go with section 20.12, preparation and reactions of amides. The amide is the least reactive group in this set, but it is the one then that can be prepared from all of the others. So it can be prepared from the acid chloride, it can be prepared from the acid anhydride, and it can be prepared from the ester. The acid chloride is the one that's most useful because it's the more reactive derivative. But you could take each of these carboxylic acid derivatives and make the amide from it. So we looked at this in the previous chapter on the acid chloride, so I'm not going to talk about the mechanism here. But this is the easiest way to do it. Take two equivalents of your amine. If you use a primary amine, you will end up generating, let's make that a different group, a secondary amide. And if you use a secondary amine, you will generate the tertiary amide. In the amide bond, and I think I've mentioned this in my lectures before, but the amide bond is a very important bond. It is the bond that holds the amino acids together in proteins, so it's also known as the peptide bond. It has some rigidity. There is not free rotation around the bond that I've circled there. That carbon-nitrogen single bond is actually got quite significant partial double bond character, and so the rotation around there is somewhat restricted. And that gives this additional, sorry, I had a hydrogen here, but it gives that backbone of a protein some additional rigidity there. So that restricted rotation plus then all of the side chain interactions and the hydrogen bonded interactions between the amides on different parts of the chain are what gives it the secondary and tertiary structure and maybe even quaternary structure, but gives it the structure and function. Of course, all of those parts are required for the protein to have the correct structure and function. So let's look at some hydrolysis reactions. Starting off, you might notice, or those of you who are more aware might have noticed, now we're talking about having to heat this bond. So it's the least reactive of the bonds, which of course is again a good thing for our proteins. In order to break this bond, we have to apply some heat, and we tend to have to use some stronger acids. So you might be using more like 6 molar hydrochloric acid and 6 molar sodium hydroxide to really get this reaction to work efficiently. Our hydrolysis reactions then under acidic conditions or basic conditions, we're going to look at each mechanism in turn. We'll start off with the acidic conditions, but again, it's almost identical to the ones we've seen before. So our first step, again, is the proton transfer. We're under aqueous acidic conditions, so our proton source is the hydronium ion. We're also under aqueous acidic conditions, so we don't have any negatively charged intermediates. So we get this proton transfer. By this stage, hopefully this type of reaction mechanism is becoming relatively routine to you because we've done it with most of these carboxylic acid derivatives already. So nucleophilic attack at the electrophilic carbonyl carbon. We've got this intermediate here with the positive charge. We need to turn the NH2 group into a better leaving group. We need to protonate it so it leaves as ammonia. So we have a set of 2 proton transfers. Oops. Let me get rid of my errant double bond there. Got a bit carried away. So now we have this intermediate. We're going to protonate here. Our old friend, the hydronium ion. So here's our proton transfer. Now that's set up as a good leaving group. So we do reform the carbonyl and kick out the leaving group. We have our protonated carboxylic acid, but we've kicked out ammonia, which is a decent enough base. It will do this deprotonation reaction like we saw for the base. No, sorry. Let me change that up. Got a little bit ahead of myself. So we do this deprotonation here, and then we have our carboxylic acid. So ignore that first thing I did. That actually will come in more useful on the second mechanism, which is the hydrolysis of the amides on their basic conditions. So this, for this one here. Okay. Let me skip forward to here to use this for the hydrolysis of the amides under basic conditions. So our hydroxide does nucleophilic attack. This mimics the basic hydrolysis of the esters. We reform the carbonyl and kick out that leaving group. Looks like it's the wrong choice, right? Because NH2 minus is a worse leaving group than hydroxide. And it may be that we're kicking out a lot of hydroxide and just kind of stuck in this equilibrium, or we have that equilibrium going on, would be a better way to say that. But if some of the NH2 gets kicked out, we have this species here now, the amide anion, and that's a really strong base, so it's really going to do this deprotonation. And that's what had popped into my mind on the previous slide, but I didn't need to use it until this point here. And so we generate that carboxylate anion, and then that's why, whoops, that's why back here we need that second step to protonate the carboxylate anion. So this one here is analogous to that saponification reaction of esters. Okay, let's look at some reactions of the amides. We can take the amides and react them with lithium aluminum hydride to generate an amine. So this is a different type of reaction. In the other ones, we ended up kind of keeping the oxygen functionality, right? So with an ester, we converted the ester to an alcohol. Here, the carbonyl group is completely removed. And we turn it into a primary amine. So we can take an amide and turn it into a primary amine. But remember, we have that extra CH2 group. Well, not really an extra CH2 group. You might see later when we talk about amines why I said extra there. But we have that carbonyl carbon, which was this carbon here, or this carbon here if I highlight it on the reaction scheme above. Okay, so this last slide just shows us a kind of summary of these reactions. We're going to take a look at this one in the next section. we're actually going to use our old friend thionyl chloride for this, but we'll look at that in the next section, the preparation of reactions and nitriles. And then this reaction here with the bromine and the hydroxides called the Hofmann rearrangement, we'll see that in the amines chapter, which I believe is chapter 22 in this new textbook. But it's not very reactive, so we don't have a great number of reactions of them. We have our hydrolysis reactions, and then the reduction to give us the amine. And we'll follow up by looking at this in the next section. So that concludes this reaction, or this section of the text.